College to watch it. BA cosine theta, great. That's changing. That's no, right? Okay. So the voltage, which they give us, is what's our voltage? 0.080 is equal to the area, which I don't know, which is a little disturbing. Okay. By the way, this would be the area of all the loops. Do you want to divide out the 40 now? Or 400 now? 50. You want to divide the 50 now or no?
Yeah.
Well, let's divide out the 50 because each one's going to have just part of that voltage, right?
We don't know what the area is, right?
Right. We don't know what the area is, so I'm going to leave the area in there. Cosine theta, it's going to be cosine of 30 degrees this way because I'm 30 degrees away from where I want to be. Right? Normal would be perfect. So 30 degrees off of that, so it's going to be cosine of 30 degrees. And then over here I got the B dt, right? Throw that in my calculator over here. I get 0.0016. Is that right? No, it's 0016. Agreed? Area 0.866. What's dB/dt? Nix.
It is 400 divided by 0.4.
400 times 10 to the negative 6 divided by 0.4 is my dB/dt. So I get 0.0016 divided by 0.866 divided by 400 to the negative 6 times 0.4. And I get like 1.8, is that right? 1.85? meters. Anybody disagree with that? Now that's the meters squared, right? Because it's an area. So how do I figure out how big how long the wire is? Square root. So I get one of the sides is equal to 1.36. How many sides would I have if I wrap this 50 times? Each one having 4 sides. Times 4 times 50, right? Times 200 total.
So did we not need to take that 50 out?
I took the 50 out right here.
We didn't, but we're adding it. Now we're multiplying it.
Now we figure out how long the wire is, right? So we're putting it back in.
We could have just left.
We found the area of 1. Oh, well, you could have, but that would make one big square, and that's technically not what's going on.
But it worked.
It'd be the same answer for the length of the wire, though. It'd be absolutely true. I got 272 meters. How long the wire is? Well, okay, first of all, I found the area, right? So I found that one side is 1.36. Now remember, this is a coil, 40 squares.
Wait, how do you get one side 1.36?
All right, 1.36. Well, I know it's a square, so that would equal the side squared, so we can square root.
Yeah.
All right.
What's the time for?
What? Time? Well, there's 4 sides to a square.
Right.
So I need 4 sides to make a square, and then times 50 squares. All right. I got one more thing to do, and I've got 9 minutes to do it in. So here we go. Brandon, one more thing to do. 9 minutes to do it in. It's an adjunct to this.
I thought we were done.
I know, but it's just an adjunct to this. Just one little extra tweak. You ready?
No.
Okay, let's do it. Okay, so we're talking emotional EMF. Go to 14.7. Oh, yeah. Now, if I were to take a bar and send it through a magnetic field, you might anticipate, Mr. Resney, there is nothing because there's no loop. But if I were to put a loop on it, what would happen? If I start sliding it this way along this, take a bar, I take a U-shaped wire and I start sliding it this way, what's going to happen? Not charge. What's going to happen? I get current, right? I'm going to get current because I'm shrinking my loop, aren't I? Look familiar? Shrinking the loop. So my voltage would be equal to what? Derivative with respect to time of BA cosine theta, agreed? Let's assume the theta is constant. Let's assume the magnetic field is constant. So my voltage would look like B cosine theta dA dt, right? Because dA dt is what's changing. Agreed? Now here's where things get fun. The distance between here and here, let's call this y. Is that changing? No. So if I were to go further and do my area formula, I might notice that this is d dt of x times y, right? But x isn't changing, is it? Or sorry, y isn't changing in this case. So I can pull the y out, and so I get b cosine theta. And by the way, y is L, isn't it? It's the length of this bar where it's touching between the two places of the wire where it's touching, right? So that would be length times dx dt. And what is dx dt in this case? Rate of shrink. That's exactly what they mean when they write it this way, but what is it in real life? Isn't that how fast the bar is moving? Right? That's how rate of shrinking, right? So this is going to be V, and this is going to be equal to BL. Oh, you're going to love this formula. V. Those V's don't cancel out. So this is voltage. This is going to be potential difference is equal to a magnetic field length, and this is speed. Now, what's interesting about this is it works really well with a wire. You can see it really well with a wire doing this. But if you just take a bar and move it through a magnetic field, by definition, it still has to have voltage. So charge will start to do what? It'll start to flow to cancel that out. So things that travel through magnetic field become charged. Okay? Not really a big deal, but something you should keep in the back of your mind for utility. The real utility is if you're sliding it along some rails, which you will see on those questions of the week. So, what are we going to do by next time? We're going to try one of these problems. I guess we're going to try that right now. Try number 1 right now.
Does anyone have to do this?
What? We assumed it was perpendicular and got rid of it. If it's not perpendicular, what are you going to have to do? Cosine whatever it is. Almost assuredly, they're going to leave that perpendicular. I think that's one more thing that's just crazy. Try the problem, Bernard. Try it. Come on. You can do it. Have faith. No, there's magnetic field isn't exactly big.
Is it that small?
Yes. Actually, that's a little large. I don't know where this is, but there's something going on there that's bad.
The mole.
Oh. Ready? Got it?
Got it.
All right. Oops. So I've got a wire. I've got it heading north. It's held east-wise. It's 10 meters. It's got 40 micro Teslas, which way is it going? Down or up? It's got to be down. Okay, well, I didn't tell you which way it's going down, but I'm going to say it's down. They'll tell you which way it is. So far, so good? Okay. So if that's my situation, I've got to figure out what is my voltage, is what they ask, right? Potential difference between the two ends. So I'm going to go voltage is equal to BLV. So it's going to be equal to 40 times 10 to the negative 6 times the length of the wire, which is 10 meters, times its speed, which, what is the speed?
30.
30 meters per second. Put it in my calculator, and I get
Hold on.
1.2 times 10 to the what? 4, negative 2 volts. So far, so good? Now, bonus round question. The important question, the question is worth just as many points to getting this calculation correct, usually on the AB test. Which side's positive of the wire?
Right-hand rule.
You've got positive, the first right-hand rule, right? You have positive charges inside this wire. We're going to pretend like they're the ones that move. They're going this way. The magnetic field is into the board, so my hand's pointing the right way. Stick out my thumb. Which way would positives be forced to move?
Left on the paper.
Isn't under the thing also going into the board?
Yes, they're both going into the board, right?
So how can you just say
The wires, but the wires being moved. The charges are moving this way, right? Because we're moving the wire with all the charges in it. And so since all the wires move, it's QV cross B, right? We're back to the very beginning, QV cross B, right? So the charges moving this direction, magnetic field is downwards. So the force would be to the left or the west, and so the positive side would be the west. Drop the mic.
Oh, that was recorded, yes.